I can record.
Yeah.
I'm recording right now. It's recording. Yeah, you can tell me. So we have D, which is the constant difference, and we have A, which is the starting term. These are the things that define arithmetic sequence. So 1, 3, 5, 7, and so on. That's what the arithmetic sequence is going to give us. And this can define this idea can define every single possible arithmetic sequence. So anything with a constant difference will have a starting term, and it will have a constant difference. Um, and sometimes, these aren't simple numbers, like 1, 3, 5, 7. It could even be algebra. For example, you could have x. So for example, you could have this. You can write the starting term as a, then the second term is going to be a plus d. Then the next term is going to be a plus 2d. And the next term is going to be a plus 3d, and so on. So what I'm trying to get at with this like idea of writing it in terms of letters is getting comfortable with the concept of writing using algebra. So instead of always linking something to something numerical, also looking at what algebraic things look like. So if I were to start with a plus d, a plus 2d, a plus 3d, just because there aren't any numbers doesn't mean that we can't spot a pattern. And the pattern that we can spot is that there is a constant d being added, and this d could be anything. It could be any variable or any constant added to any starting term. And it's just about getting comfortable with the concept of the fact that algebra can be easily mixed into these things. So now let's think about a little bit of analysis as to what the arithmetic sequence actually looks like. So we referred backward before to a UN, right, which is essentially a uh, trying to find a formula to come up with the nth term of the sequence. So let's think about the information that we're given. First of all, we know. So let me just move out a bit and move this here. So we're trying to find what UN is using the fact that the starting term is going to be A and the constant difference is going to be D. And we don't need to, we're going to refer to this numerical sequence over here, but we can use any sequence. And I'm just trying to like refer to the numerical sequence so that there's some context. So we know one thing, which is that U1 is equal to A, correct? So that means that when you plug in 1 into n, you should be getting A. So we can start off writing a little. So we know that fact. Then we know that U2 is equal to A plus, no, not 2, sorry, is A plus D. And we know that U3 is equal to A plus 2D. So what? What you're going to see is that there's a pattern. First of all, there's always A, and that doesn't change. There's nothing in front of the A changing it. There's nothing changing the fact that it's always going to be an A. So we can come up with the start of what the sequence might look like, which is we know there must be starting with an A. And then what we know is there is a D, and the factor in front of that D is changing. And note that even though in the U1 sequence there wasn't a factor of D, we know that there still is a D over there, but just with a zero factor in front of it, that the zero multiplied by the D cancels it out. So you start with 0D, then 1D, then 2D, which is then interesting because now you can put in a D sequence. So you know there's a D, but there's something in front of that D, and what should that be? There's something in front of the D, and what should that be? So that's going to be,
And
yeah, Donato?
wouldn't it be the number of the term you're in?
Yes, exactly. So
-1.
yeah, so
Sorry.
one would think, yeah, obviously n. However, it's not going to be, we know it's not going to be n because if we look at U1, if you plug 1 into n, you end up with 1, which means that you would have A plus D, which is not what we're looking for. So yeah, you're correct
1.
in saying A plus n minus 1 times D. Correct. So this is what the general form of an arithmetic sequence will always look like when you're having when you in this scenario. This is a general form, but you don't need to memorize this general form because it's important to know that you can always come up with this general form on your own. And if you just think about this in terms of 1, 3, 5, and 7, you know that there's a constant difference of 2 being added each time. You know you're going to start off with, so you know your UN is going to be starting off 1, that's your starting term, plus your constant difference, so that's 2, to n. But you know that the n starts a little, is offset by 1, so it's n minus 1. However, you can actually, in this specific scenario, you can actually simplify it a little bit. It's not necessary to do so at all times. In many sequences, it may not be simplified, like you can simplify it, but over here you can simplify it. So I'll go ahead and do that and just show you what the sequence actually looks like. So I'll multiply by 2 by both of the terms in the binomial. That's 2 times minus 1, that's minus 2, and that's equal to 2n minus 1. And that's going to be basically going to give you your, that's also what that's what the sequence is. And this is the sequence of all odd numbers. So that's an arithmetic sequence. And now I'll do, does anyone want to take like a screen capture of this if they like? You can go ahead and do that, but it's
Yeah,
recorded,
sure. Give me a
so-
second.
Yeah, just take 1 minute. Why are there hearts everywhere on my screen? Can you guys see this?
Oh, because
Yeah, because we love you.
someone annotated on your screen.
Who? Oh, okay. I see, I think I see what's happening. I don't know how that works. It's definitely Donato, isn't it? No, Donato, stop. No, Donato, what the hell? There's 11 people here?
It isn't me. I don't even know how to do
would
it.
draw hearts if he had the chance. He would be drawing like dicks. Okay.
Yes, exactly.
Oh, jeez, please
Like this
don't.
cannot be Donato, and Donato wouldn't say ooh. Okay.
Okay, so are we done with everything? Donato, can you stop?
It isn't me. I'm making a folder for the screen caps. And eating popcorn.
Wait, 1 second. I'm gonna disable participants' annotations. Yeah, you guys just got screwed.
Yeah, okay.
That's arithmetic sequences. I'll go back and look at another property in arithmetic sequences right after I'm done explaining. No, I'm not gonna give you remote control of my screen. I'm gonna kick you out, Donato, if you ask me again.
Okay, I'm sorry. That was the word.
Okay, the next type of sequence to look at is a geometric sequence. I'm not exactly sure why they call it a geometric sequence. It doesn't actually have anything to do with geometry. I'm inclined to believe it's got something to do with complex numbers. But that's for another day. But a geometric sequence is essentially when you're multiplying something by a constant difference instead of adding it to a constant difference. So in this scenario, you would have a starting term 1, then go to 3, then go to 9, then go to 27, and so on. I don't know what 27 times 3 is, whatever, it's fine. And that's what a geometric sequence looks like. And again, we can identify some key properties of the geometric sequence. We can identify that there is a, which is our starting term, which again can be denoted as u1. And we have a constant, but this time we're going to call the constant r instead of d to indicate that we're actually talking about a geometric sequence and not an arithmetic sequence. So we would start with r, and that's our new constant difference. But it's important to know that this constant difference is being multiplied. It is a multiplying constant difference. And in this scenario, we would indicate that it is actually we're actually
Wait,
going
like,
to do,
isn't it called the constant ratio?
yeah, the constant difference, constant ratio. I guess, yeah, you're right. It should be ratio. That's why it's
Thank
called
you.
R.
I'm just making sure.
Yep, ratio. Yep. I don't think it's necessarily that important. Just note this is R and that's D and that's
I
different.
think you should let him annotate your notes.
No, I don't think that's a good idea.
I agree. Give me control.
Algebraically speaking, what we can denote this in the same way as we did before is if we start with A, our next term is going to be A times R, AR. Our next term is going to be A times R squared because we have A times R, and so on to AR cubed and AR to the power 4 and so on. This is a new way to describe our sequence. And again, we can find a pattern quite simply. So first of all, if we're looking at UN, we first try and understand what is our we have a thing that's always in every one of them, an A. We also know there's an R in every single one of them, and this R is being taken to some power. And that power, again, like the previous time, we would think that it would be n, but note that in U1, which is A, n is actually, there's actually no R, so we know it's going to be n minus 1, like we did before. And then this is our general form for the geometric sequence. So exact same concept, but this is our new general form for the geometric sequence. Now, I would like to just pay close attention to the fact that like why exactly I was showing these algebraic forms is because sometimes you get asked questions where you're meant to describe things in terms of this algebraic form. So if you were to look at A, a plus d, a plus 2d, and so on. Sometimes what questions will ask you is, you know that the first term, the second term, and the third term are some number. Like if we say like the first term, then the third term and the fourth and the fifth term. So like the first term is like is 6, and then the third term is like 8, and then the no that's let me think. I'm not gonna start with 6. That's a big number. 8, and then the fifth term is like 32. And then they want you to try and figure out and they say it's a geometric sequence. It's a geometric sequence. And they need to try and figure out what exactly is your what is A and what is R. They ask you this very commonly. So one way you could do this is look at your sequence, your general form of the sequence in algebraic form. You know, it's always going to fit something looking like this. So what you can do is that you can look at, this is your first term, this is your third term, and this is your fifth term. And you know that A is equal to 2. You know that AR squared is equal to 8. And you know that AR to the power of 4 is equal to 32. Now, A is equal to 2. That's a pretty simple fact that you now have in your toolbox. And you can make that, and then you can apply that over here to show that R squared is equal to 4. Since we make the A is to replace the A with a 2 and make it 2R squared is equal to 8, and make that R squared is equal to 4. And this one can be replaced with as R to the power of 4 is equal to 16. And then you can then obviously you can see that R is equal to 2 from both of these equations. Note it could be R equal to 2 or negative 2. And that's something that they could also ask you. So they could ask you what are the two possible ratios. And in this specific scenario, you see that there are two possible ratios, 2 and negative 2, because R squared is equal to 4 can be with 2 or negative 2, and R to the power of 4 is equal to 16 can also be with 2 or negative 2. And that's another possibility. So I just want to like expose a little bit to this possibility of questioning where you might need to try and substitute and use some algebra in order to solve for what the sequences could be, which is probably for SL going to be the hardest thing that you probably need to do. And obviously you can do more practice problems for that, but I won't go too deep into what the practice problems are. And now I just want to like explain simply so now we've looked at what an arithmetic sequence generally looks like, what a geometric sequence generally looks like. We can look at sums, because that's the next thing that we look at, is how to take the sums of them, and then also how to take the series of them. And a sum is basically just it's just the sum of a certain number of numbers. So a sum is basically, in this context, a sum is where you take a finite n number of things and you add them up together. So like 10 or 12 or 13, like some finite number. And a series is when you add up the infinite number of terms. So you add up all of them, an infinite number of them, which is what a series means. It's like an infinite sum, essentially. So here, the sum notation uses something called sigma notation. And for some reason, I always see that people get very confused with sigma notation. But what sigma notation really is this little sign. And there's going to be some number in front of it. So let's just take an example like 2n plus 3 or something like that. And what the sigma function does, it really is like a function machine essentially. And what it does is that it adds up things with a certain instructions. So what the instruction is that you need to take this formula, which has some variable inside of it, n. You're going to start adding at n equals to 0. Actually, no, not n equals to, let's start with n equals to 1. You're going to start adding at n equals to 1, and you're going to go up to some number, let's say 10. Okay, so what it says is that what you need to do, what you're telling the sigma function to essentially do, is that you need to take this, plug in 1, and then have that at the start of your sums. Then you're going to have, so you're going to have 2 times 1 plus 3. And then you need to add n equals to 2, which is one step higher towards 10. So you have 2 times 2 plus 3. And then so on until you reach 2 times 10 plus 3. Essentially, it's running through each of the numbers between 1 to 10. So it's going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as it's doing that, it's plugging it in into the formula that's been given in order to like show that this is into the formula that's been given to create a sum of several different numbers. And this is essentially this is just what sigma notation is. It isn't something complicated, or it really isn't even something to go out and learn as a concept. It is a tool. It is just to help you figure out how to be able to do things and how to add things. And obviously the sigma notation is very useful when you're looking at a sequence. So for example, let's go back to our arithmetic sequence. Un is equal to 2n minus 1. Sorry. Oh, okay, whatever. I don't know what is happening. My laptop is dying. Okay, so un is equal to 2n minus 1. And then, oh, I'm forgetting. What am I doing? Arithmetic sequence, I'm summing them. So un is equal to 2n minus 1. And that's our sequence, 1, 3, 5, 7, so on. And essentially, what if we wanted to sum the sequence until a certain number of terms? And the sigma notation comes in very handy, because what you're trying to do is, if I wanted to add up these first four terms, 1, 3, 5, and 7, I would just add 1, 3, 5, 7. But what if that's some ridiculous sequence? Like it's massive, there's like crazy numbers, I need to sum up to 1,000. How am I meant to do that? And essentially what I can do over here is if I have 1, 3, 5, 7, I can add up, it's going to be 2 times 1 minus 1, then plus 2 times 2 minus 1, then plus 2 times 3 minus 1, plus 2 times 4 minus 1. So that's all of the terms laid out. Or I could just write that as starting at n equals to 1, up until to 4, you need to do 2n minus 1 and add up all of these, which is equal to our sum, which would be 16. Which is decent. That's what we're meant to be doing over here. And the way and essentially you need to find quick ways in order to like represent the sum better. So let's think about the general form which we had earlier. Let me think about this. Okay, so our general form earlier was a plus d, a plus 2d, and so on. Actually, I'm going to put in another term there just to be able to check. Sure. A plus 3d, and so on. Now we're going to think about summing this together up until the nth term. What is it actually equal to? Because we did a sum with 1, 3, 5, 7, but the only reason it was easy to do that sum was because we need the numbers. But sometimes you don't know the numbers. It's like in an algebraic form like this. And you want to sum up till the nth term, until an n number of terms. And essentially the way that you would do that is you would do this. So we have a plus d, we have a plus 2d, we have a plus 3d, all the way up until our nth term, which we need to add up. So a plus nd. And then what we do is we can add up whatever we can see. So we obviously we can see that there's a sum up of a's. So we have na. One second, give me a minute. I haven't thought this before, so I'm like, I think I might be doing this wrong. So I just want to make sure I'm not doing this wrong. Yep, that's fair. Yeah, I think I'm doing this correct. Yep, that's correct. Here, so we sum up all the a's, we get na, and then we notice for all the d, we sum up all the d's. Again, it's going to be nd. There's going to be nds, which are added up. Wait 1 second. Wait. There's 1, 2, 3, oh, wait a second. 1, 2, 3, NAs, NAs, up until n, 1, 0, 1, 1, 2. Wait a second. I'm a little confused. 1 second. That's 4 terms. 1, 2, 3. Oh, okay. So we need to check. We need to count how many D's there are. And there are actually only there's n minus 1 D's over there. Because there's an n number of a's right over here. There's a. There's like n terms coming down from here. But if you count the number of d's, there's d's, then 2d, then 3d, then nd. But it doesn't start. There's like 1 less than how much the a has. So essentially, it's 1. So it's going to be 1 plus 2 plus 3 all the way added to n minus 1. times d. That's how many d's there are in this sequence. I have a feeling it's gonna go Ori, and that like this is gonna be too confusing. And if it just get too confusing, and it's already too confusing, can you tell me? Okay, I'm gonna assume deafening silence that it's not that confusing. No, Donato, just stop being annoying.
What do you mean? I haven't done anything.
Okay, whatever. Wait, I need to think about this harder. I'm
By the
thinking
way, are
about.
you sure it's 1 plus 2 plus 3, or is it just n minus 1?
It's not n minus 1, because you can see very clearly there's d, and then there's 2d, and then 3d, and you're adding up all the d's. This itself is an arithmetic sequence inside the arithmetic sequence sum. And honestly, at this stage, I don't think I have the capability in order to like directly be able to tell you exactly, exactly like how to solve this specific arithmetic sequence of 1 plus 2 plus 3 all the way to n minus 1. But what I would tell you is that there is a way to do it. And that way to do it is what is it? I forgot. Oh God.
You add the sequence together with itself.
No, you don't do that. You do it's n times n minus 1 over 2 or something like that. It's like
Yeah,
it's
but
like,
to find that formula, you can add the series together.
really? What does that mean? What do you mean?
Like 1 plus 2 plus 3 all the way to n, then you
Yeah.
add that together. Add it together, or something, or subtract it or something. Then some stuff cancels out.
Yes, you're correct. Yeah, I think I know what you're talking about. Yeah, so yes, you're right. They did that in the number file video where they messed up the negative 1 over 12. Yeah, okay. So if you were to call the sum 1 plus 2 plus 3 plus all the way up until n minus 1. Again, if this is getting confusing right now, just don't listen to it. It's really horrible. But I'm just trying to like explain exactly what I'm going to do over here. And I hope that everyone's still following. I'm basically trying to figure out what the sum up until the nth term looks like, and showing you the exact derivation for it. If you don't understand, I'm very sorry. Yeah, you're right.
What kind of philosophy is that?
What am I doing? I'm still getting like weirdly confused.
If you don't understand, too bad.
No, this shouldn't be this confusing. Wait.
Okay, babe.
Not only are you confused, I mean, if
Yeah.
you're the one that's confused, I mean,
No,
we have
I
a
don't know.
problem.
This is not meant to be. I've done this before many times. This is just.
I'm beginning to doubt that.
Wait, Aryan, can you speak and just like guide me through it?
So,
Are you having some?
Wait,
So
what are
you're
you
ra-
trying to do?
I'm basically trying to get this into a form which can be a formula. Because right now this is a 1 plus 2 plus 3. You can't just keep adding 1 plus 2 plus 3 all the way to n minus 1 every single time you want to do this. So I'm just trying to like come up with the formula for the sum.
you're trying to derive the AP formula, right?
Yes.
So what you basically do, you write the same series again, but in the inverse order.
Like this.
Yeah. And then you add both of them up.
Okay, so you get 2s is equal to n all the way added to n.
2 plus n minus 2 will also be n, and it will be basically n that many times.
Oh, okay, yeah. It's gonna be n plus n plus n. And so on. Everything's gonna be equal to n. Yeah, okay. And then that means that 2s is equal to n times n minus 1. There. And then that proves that this sum is equal to n times n minus 1 over 2. Does that make sense to everybody?
One question: why is it that you're flipping the formula? Well, not
Okay,
the formula,
once
but
you
the
flip
series
it,
of this
okay,
series.
once you flip it, this is what you can do. One second. I think it'll make more sense if I do this in like if I show more terms. If I do n minus 2 plus n minus 1, like if I add those two terms, I think it'll be easier to see. Here. N minus 2 plus n minus 1 plus down to 3 plus 2 plus 1. Okay, now, so the n minus I'm going to start n minus 1, sorry. So n minus 1 adds to the 1 and gives you n. The n minus 2 adds to the 2
Late.
gives you n.
It's n plus 1, not n minus 1, because if you oh no, sorry, this is the first n minus 1 numbers, not the first n numbers. Sorry.
Yeah. Yeah. So the first n minus 1 numbers, that's what's n minus 1. That's n and n minus 1. It would have been n and n plus 1. Yeah, I know what you're saying. It's an n minus 1, n minus 1, n. The n minus 2 and 2 will give you n. And then on this side, the n minus 2 and plus this 2 will give you n. And then n minus 1 plus 1 is going to give you n. So you're just going to have a series of n's. And how many n's you're going to have? You're going to have n minus 1 n's, because you had n minus 1 terms. So that's why you could do, there's how many n's are there? There's n minus 1 n. So you do n times n minus 1. So the sum is equal to n times n minus 1 over 2. So then, if you go back to our little formula over here, we have NA plus n times n minus 1 over 2 times d. And then, this is exactly written over here, by the way. So it's going to be, if you can factorize out the n, we get a plus n minus 1 times d over 2. But in order to make this a little more friendly, what the formula booklet does is that it says that you're going to have n over 2 times 2a plus n minus 1 d. And that's equal to the sum from n equals to 1 to n of a plus n minus 1 times d, which is equal to just the denoted by Sn. That's the sum of the arithmetic sequence. That's how you prove that. The proof isn't necessary. The formula is necessary though, and thankfully it's in your data booklet. It's right over here. If you ever need to figure out what the actual sum of the sequence is, you just look at the data booklet and you'll be able to see how to sum the first n terms, and you just plug it in. This is an alternate form over here, the one with u1 plus un. That's also something that could be easy sometimes, because sometimes they'll tell you this is the first term, this is the last term, and then multiply that by how many terms there are, like n over 2. That also works. So either one of these formulas will work, and you can just do that. Yeah, you can do that. That's you'll do fine. And use what?
UN is the last term, right?
What?
UN is the last term, right?
Yes, un is the last term. Well, un is the nth term. So if you want to like look at 5 terms, then un is the 5th term, and that would be the last term you're looking at. Yes. Okay. The same thing is it can be said for the geometric sequence. I'm not going to do the proof for the geometric sequence. It's a lot more difficult. There's like it's a little more confusing. Like the algebra that's used is from the binomial theorem, and you haven't learned the binomial theorem yet. So I don't think I want to like look at that yet. So yeah, the sum of the geometric sequence is written over here. U1 times r to the power of n minus 1 over r minus 1. So if you want to check ever what it is, if you know what r is, you know what u1 is, you can plug it in and check over here. And I think that's why for a lot of this I was very like keen in explaining the fact that there is an a and a d, or like a u1 and a d and a u1 and an r, so that you can use these formula to the best of your capability. So if you forget about series and sequences, all you need to do is look at these formulas and think about what these formulas are saying, and especially just look at what does d mean, what does r mean, what does n mean, what does un mean, and if just to quickly recap what all those things mean. Un is the, oh sorry, that's erasing differently. The nth term of the sequence, the nth term. D is the constant difference. R is the constant ratio. N is like again for the nth term, whatever you're looking at. And yeah, that's that. And that's all you need to know for this part over here. And yeah, that's everything you need to know basically about series and sequences. And obviously we can, yeah.
Sigma notation?
What, you have a question about sigma notation?
Yeah.
Okay, sure.
Well, wouldn't you be able to have like multiple answers for how to make a segmentation for a series or something?
Yeah, you could. And I can show you an example of that as well.
Yeah. So, but then in that case, if you have that on the exam, is there a right or wrong answer? Or as long as you put something that makes sense, you'll get it right?
No, I mean, as long as you put something that's mathematically correct, then you'll get it right.
Yeah, even though there's like many potential answers, it's fine.
There are many
Like,
different answers. If they want one specific answer, there'll be something indicating they want that answer. Usually, I think what happens with sigma notation, they'll be like, show that this sum is equal to this sigma notation or something like that, or you can put whatever answer that's mathematically correct and you'll get it correct. If your teacher ever says that you're wrong because you didn't put the exact same sigma notation, then tell her that she's wrong and that your one's right as well. Okay.
Wait.
Okay. Like
This can happen with like literally anything. Like if somebody tells you that your general term is -3 plus 8n or something,
yeah.
then you can say that you're starting with 0. And
yeah, exactly. Yeah. So
but then you can also say that the general term is -11 plus 8n, and then you can start with 1.
Yeah, you can start with whatever. So like you even look at the sigma thing, right? If you start at n equals to 0, so let's look at just our simple sequence. So we had like a plus n minus 1 times d, right? If we start at 1 and go up to some k, it's going to look like this. But if we start, if we had the formula as a plus nd, like that, then if we start at 0, we can just go up to k minus 1, and it's the same thing. These two are the same thing. The n minus 1 is offsetting it by 1, so you can start at 1. But over here, if you wanted to start at 0, you don't have to have the n minus 1 anymore. You can just have the n, and then you only go up to k minus 1. Just to make it a little easier. Don't have to lose the k. If you're going up to 10, this one is just going up to 9, and then you'll
so you can do both.
So you can do both. Both of these are the same thing. Yeah, as long as your function is correct. Because like if you understand the sigma notation well enough, you'll know that these are both the same thing. Because the 0 to 9 is 10 terms, and the 1 to 10 is also 10 terms. And essentially, it's about where you're starting at. And if you do n minus 1, you're starting at 1. If you're starting at 1, you need n minus 1 so that the 0 is there in front of the d. And if you have starting at which is n, then you need the 0 in front of the d, so you can plug it in like that. So yeah, they're the same thing.
wait,
Okay.
like I have a question.
Yeah.
So when you were showing us the formulas to sum up geometric sequences, why is it that there were two versions with one where they
Okay,
flip?
I'll show you. I'll show you. I'll show you. Also, Donato, there's a HL session tomorrow where I'll explain this in like greater detail and also do proofs so that you can like.
Is it at 4 again? Is it at 4?
Yeah, it's the same time tomorrow, but I'll do the I'll do the proper proofs so that you can understand you can also practice proofs with induction and stuff.
Yeah. Okay. Thank you. I'm just showing up to both in case.
Yeah. Here, the reason it's flipped is basically this. So if I had like, so let's just look at this. I can just do this really quick and show you how it flips algebraically. So r minus 1. What I can make that is I can take out a factor of -1 from it. I can just make it -1 times a1 times 1 minus r to the power of n. Do you see what I did there? I took out a -1 because like r to the n minus 1, and then I multiply both by -1. I'll get 1 minus r to the n.
Mm-hmm.
So I get 1 minus r to the n over r minus 1. And then the -1 is over there, and I can just like make the bottom negative instead. And if I make the bottom negative like that, then I'll just end up with a1 times 1 minus r to the n over 1 minus r. That's all. I'll look into this in more detail tomorrow because when I'm doing the HL session, I'll show the proof of the geometric series as well. The sum,
Okay.
but the proof isn't necessary for SL, so I don't see the point in doing that. So there's also compound interest, which is there in this topic, but really even compound interest isn't necessarily it's just a form of the geometric sequence, and as long as you understand that it's just a form, what is it? Yeah, okay, we sent an attachment. Okay. So the form of the geometric sequence is just that's just what the compound interest formula is. So you start off with some foundations, some principle. I'm not sure what they call the principle over here. Why do they call it PV? Okay, whatever. So PV is the principal value. So principal value. And what the principal value essentially is U1. That's the starting term. And that's all. So, and the next thing which they look at is R. So R is the R is the constant ratio. Constant ratio. However, it's a slightly modified constant ratio because there's a small issue with this R. Say if I started with 1,000 and I said that my R, which is over here basically an interest rate, is 2%. I don't actually have to multiply the principal value, PV, by 2%. That's not what I do because that's just going to give me like 20. And that's not what I wanted anyways. What I really want is to add, what I really want to do is I want to actually make it 102%. So if I multiply 1,000 by 102%, that incorporates the original value of 1,000, then plus the 2% interest on it, which will then give me 1,020, like I need. So really, this R, you need to be really careful about this R. And essentially what this R actually is 100 plus R is the actual interest rate, which you're being multiplied by each time. And then the other term which you have is K, which is the number of compounding periods. The number of compounding.
So, over time, does the compound interest function, it becomes an arithmetic sequence and a geometric sequence?
No,
right?
it's just a geometric sequence. There's no arithmetic sequence. You're multiplying by
But you add the initial amount.
Yeah, so the R that's been given,
Yeah.
so you need to add the initial amount, but you can incorporate that into the ratio. So you don't need to add it like manually each time. So yeah, that's what's the thing. That's what it is. The formula looks really complicated, obviously, because you have like the compounding period, you have like the N, which is how many number of years in the future, and the K, number of futures. It gets very confusing. But to give you a very simplified version of what the compound interest thing looks like, we can start with, if you just start with some value PV, and then you go to some, and then after like, so I say after 1 month, say you're compounding, you're compounding 12 times a year, and yeah, you're compounding 12 times a year. So after a month, you're going to end up with PV times 100 plus R, right? And then you end up with PV times 100 plus R times 100 plus R, which is going to end up being 100 plus squared, and so on. Oh wait, 1 second. I should indicate this is a percentage value, so I'm going to divide this by 100 over here. Because it's a percentage value, it's not, you're not multiplying by actual numbers, you're multiplying by percents. So 100 plus R is an interest rate, so it's a percent. So you're going to continue doing this forever. And essentially what this looks like, you're going to end up with, after 1 year, you're going to end up with PV times 1 plus R over 100 times times K. Which is 12, so to the power of 12.
To the power of K.
Yeah, to the power of K. That's how many times you have to do that. And you can see it's kind of looking a little bit like this now. You have a K over there. And the other important thing is that R is actually an annual interest rate. So each time, every month, you're not actually multiplying by the whole 2% or the whole 10%. You need to divide it by 12. And that's why they have a K in the bottom, in the denominator here as well. And then they do this over a period of several years. So they add an N over here as well to show this happens several times over many years. And that's where the compound interest formula comes from. It's basically a geometric sequence like glorified. And you can see the PV is like a starting value. The 1 plus this whole thing in the center is like a constant ratio. And then the Kn is like showing you how many times this is happening essentially. The IB would be well suited to actually have like made this formula look very similar to the previous formula, like this one right over here. And they should have tried to make this similar so that it's consistent. But they didn't do that because they want to try and confuse you a little bit to show you that there's like these big values like nominal and stuff like compounding periods. So you get really confused, but it really isn't like a specifically confusing concept. As long as you understand the concept of compound interest in terms of like finance, you'll be able to understand that it's just a geometric sequence. And yeah, that's that topic. By the way, I'm not going in terms of the IB topics. I'm going in terms of the school topics. So that's why I'm not going the same things. That's the application. So that's the interest rate is the main one. The final thing I'm going to look at is the binomial theorem. And what that looks like. So essentially, what the binomial theorem does is that it's trying to figure out what the expanded sequence of a term is. So if I had, is everyone still like listening and participating? Because I feel like I've just like messed up on so many levels that no one is bothering to even listen anymore.
No.
It's 50-50.
No.
50-50. Okay, that's fine. That's okay. It's okay. We start off with a plus b to the power of n. We want to figure out what is this going to give us. And clearly, what we can see is that, let's just try and see what this looks like if we try a few different terms. So if we do a plus b to the power of 1, we're going to get a plus b. If you do a plus b squared, you're going to get a squared plus 2ab plus b, right? When you're doing your you're multiplying out. If you do a plus b cubed, I know this, it's a squared plus 3, it's a cubed plus 3a squared b plus 3ab squared plus b cubed, and so on. And obviously this looks like there's some kind of pattern happening over here, but the issue is that we don't really know what the pattern is yet, but there's a way to figure out the pattern, and that's using combinatorics. And basically it's using a concept in combinations. So let's think about why combinations actually comes into use over here. And especially it's with reference to how many different combinations you can have for a certain thing. So let's think about this. So we have a plus b times a plus b. I'm going to draw this a plus b n times, n number of times. Let's say it's n number of times. You have an a plus b and you have another a plus b, and so on. You have n number of these a plus b's. You have n number of a plus b's. And basically what this combination problem is trying to come up with is trying to figure out what the coefficients are in front of these things. So we have in a to the n term, obviously. Then we have an a to the n minus 1 term times b, which is another thing which we saw, which was that the a term power started decreasing and the b power started increasing. The an term is there. And there's the a n minus 1 times b term. Then there's the a n minus 2 times b squared term, and so on. But what are the coefficients in front of these things? And the way that you would find the coefficients in front of these things is by basically counting how many times you get one of these terms. And let's think about this, a to the power of n. What is the only way to get a to the power of n? And we know there's only one way to do it. And that's to multiply this a at the start, is to multiply this a times this a times this a and times this a. All these a's in the front need to be multiplied perfectly in order to get an a to the n. If you took up any of these other terms at all, then you're going to end up with you're not going to end up with an a to the n alone. So you know there's a 1 in front over here. Now another thing which you can do is that you want to try and figure out when is there all the a's but only one b. The way that you can do that is that say you took this a, you took from here you took this a, from here you took this b, from here you took this a, and from here you took this a. So you had all these different combinations that you have. So you could take many combinations. You could take the b from here, the a from here, the a from here, the a from here. You can take the b from here or here. You can take the b from an n number of positions. So what you're basically doing is that you can, from n number of positions, you can choose one. That's n choose one. Then for over here, for out of n positions, you can choose 2 to get the b squared, and so on, all the way until you end up with 1 times b to the n, symmetrically, the same way. And that's where the choose comes from, because you're basically trying to choose all the different possible combinations. And a quick way to further enforce this is look at this term over here, n choose 2. What that means is that you can have all the a's, but you need at least 2 b's. So this one can be, you can take this b over here and this b over here, and these ones you can take the a's. Or you can take this b and you can take this b, and this one can be a's. Or you can take this one as a b and this one as a b, and this one as a. You can take any 2 b's from these n different combinations, and that's why you choose n choose 2. And that's how you prove it's n choose 2 for the binomial theorem. And then if you want to simplify what this theorem looks like, it's going to be an. It's going to end up, again, you need to use sigma notation for this. And we're going to look at, I'm going to copy paste the formula. So surely the formula is in here. Yeah, here. No, why did they not show the closed form? Okay, in the last syllabus they used to do that. Okay. So this is what it looks like over here. Okay, and essentially note what they've done over here. So they have an an term, they have an nc1, a minus 1, this is the second term, and then they have this general term in the middle. So if you wanted to figure out when is a to the power of 6 and or something, so like say for example you had a plus 2 to the power of 7, right? And you want to figure out what is the a to the 5th term, right? What is a coefficient in the a to the 5th term? The way that you would do that is to look at this general form over here. You know that your form is going to have n choose r. I'm using a different notation with the bracket instead of the c because I prefer this one, but it means the same thing. So n choose r, a to the n minus r, b to the r. And what I need is that I know that n is 7, so I can replace the n over here with 7. So I don't have to worry about that. So I can replace the n with a 7, and then 7 minus r, and I want a to the 5. So I need a to the 7 minus r to be a to the 5. So that means I also need to get rid of the r over here and replace it with a 2. And then I can replace everything with 2's. And once I finish doing all of that, then I can use this formula over here for the choose, the 7 factorial over 2 factorial times 5 factorial. And the b squared, the b is actually just 2 over here. I can replace that as well. So I get 2 squared times whatever the value of 7 to the choose 2 is as my coefficient, and that's how you would use this. Sometimes what they'll do is they'll give you some variable, right? So they'll say that you don't know what this is. Say you have some x, you need to figure out what x is, and the x, you can put this x right over here, right? You can put the x right over there, and they'll say the coefficient is actually equal to 10. Or something. So x squared times 7 choose 2 needs to be equal to 10. So that's how you basically figure that out. And as long as you understand what this general term in the middle over here looks like, that's all you need to know for the binomial theorem. And yeah, note that this is a algorithmic process. It's not something that you need to like solve or something. It's usually just something you need to show that I can do this like this, and this is all I have to do. And I would strongly recommend using the choose stuff. And like knowing the choose and like the combinatorics and use this formula. Oftentimes what people will do is that instead of using the choose, there's a neat little feature where you can use the Pascal's triangle. So if you make a row of ones in a triangle, like so, and you add these two terms, you get 2. You add these two, you get a 3. You add these two, you get a 3. You can keep going. You can add a 4, you get 4, 6, 1. And if you end up doing this, you'll know that this series of coefficients. So if you were to have a plus b to the power of 0, you would use these coefficients. If you had a, oh, 1 second, sorry. Yeah, so if you had a plus b to the power of 0, you would use this coefficient 1. If you had a plus b to the power of 1, you're going to use these coefficients. If you have a plus b squared, you're going to use these coefficients. A plus b cubed, you're going to use these coefficients. So you don't have to do the choose thing necessarily. If you have something small, like a plus b squared, a plus b cubed, even up till a plus b to the power of 5, it's all right. Like that's okay. You can continue to using the Pascal. You can continue to use Pascal's triangle. But sometimes it gets very long and very confusing, and you could have like a plus b to the power of like 20 sometimes. And then how are you meant to figure out what the specific number in the middle is of a certain binomial, of a certain term? And then it gets very confusing. So I would strongly recommend using the n choose. In almost every SL test I've seen, there's always been some question regarding like, just take like, it'll just give you like 2x plus 3 or something to the power of 8, and just like write it down. Like that's all. Like I've seen that happen. But then sometimes it'll also like put a variable or something inside that, and they'll try and like, they'll say, okay, this term is the coefficient of this. Try and find out what the variable is. Just write out what you know and write out what the general term is at that point. and then try and solve for it. That's all. If you have any questions, you can ask now. I think I'm done. Yeah. I think that's all I'm going to look at. Yeah, that's all I'm going to look at. Oh, I should also comment. This is SL. Is this SL? Yes, it is SL. Yeah, one final thing which I need to comment on. The sum of an infinite geometric series. So if you want to add up a geometric series up to infinity, you need to make sure that you use this formula over here. And it's U1 divided by R minus 1. Again, there is a proof for this, and I will show this proof tomorrow in the HL session, but it's not a SL material. So S until infinity, the sum until infinity, you take the starting term and divide it by R minus 1, which is, and that's you're going to figure out what the infinity is. What's important is that the R is not greater than 1, because if R is greater than 1, that means you're going to go up till infinity. The sum is not going to be convergent. The sum isn't going to be a value. So if you start at 1 and then you have 3 and then you have 9 and then 27 and 81 and so on, if you keep adding all of them up, you're going to get an infinite number because it's like infinitely large. But if you were to start with something like 9 and then you're going to add 3, then you're going to add 1, then you're going to add a 1/3, then you got a 1/9, it's getting smaller and smaller. So you can basically add up into something. And that's how you do it. You use a sum of an infinite geometric sequence right over here. Again, you should be familiar with all these formulas over here. So you should be familiar with all the sequence formulas over here and understanding what all the different terms are. You should be familiar with this, the principal value, the future value, the R is an annual interest rate, the K is a number of compounding periods per year, and then that N is how many years in the future you're going to be going to. The sum of the infinite geometric sequences here. Again, you should know that this is the first term. This is R is the constant ratio, and then the binomial theorem and how to use it. And that's it. That's all. Is there anything else anyone wants to do?
You're a bad teacher. That's all I want to say.
This is like my first teaching lesson. Please don't attack me.
Like, will you be doing teaching sessions for all the topics? Or
yeah, I will slowly go through all the
sequences?
topics. Yeah, I will.
Okay. Thanks. This is useful.
Yeah, hopefully the next ones are a little better. They're better. They'll be better. Don't worry.
I don't think anybody's complaining except Donato.
Yeah, I agree.
No, I'm complaining. I feel like I.
Daughter should do the next lesson, honestly.
Yeah, let me teach them.
Okay, so I'm done, guys. If you guys want to leave, that's okay. I'm gonna stop the recording now.